In this lecture, we will introduce ourselves to the concept of Fourier integral and the Fourier transform. Let us recall our motivation in discussing the Fourier series. We recapitulate that a characteristic property of a linear time invariant system was that if it is driven by a sinusoidal excitation, the response will also be sinusoidal in character. This particular property is valid only for sinusoid. No other periodic function will have such a characteristic, will provide such a characteristic. And once this particular property is satisfied, we brought in additional concepts like frequency response function, impedance and admittance concepts, which will simplify the analysis of linear systems driven with sinusoidal excitation functions. Now, this naturally led us to inquire how we can analyze a linear system when it is driven by a periodic non-sinusoidal excitation function. And the Fourier series came in very handy in that context, in the sense that any non-sinusoidal periodic function can be thought of as composed of several sinusoids of different frequencies, and by virtue of linearity principle we can find out the response to each one of these excitation functions and superpose the responses to get the total response under steady state conditions when the linear system is driven by a periodic but non-sinusoidal excitation function. Naturally, we would like to see whether this analysis can be carried forward to a case when the excitation function is no longer periodic. We will call such excitation functions aperiodic functions. So, when a function is aperiodic, is it possible for us to consider that aperiodic function as composed of different sinusoidal functions of different frequencies? Surprisingly, the answer is yes, and this constitutes the discussion, the subject matter of our discussion under the Fourier integral and Fourier transform methods. I use the word surprisingly not without justification, because when Fourier proposed that any aperiodic function can also be thought of as composed of several sinusoids, it did not gain immediate acceptance from all mathematicians. And actually, the fact that a periodic function can be composed of several trigonometric functions of different frequencies appears to have been known even before Fourier, even though the earlier workers did not carry out this analysis to a logical limit, logical extent. But it is a singular and unique contribution of Fourier to have extended this kind of analysis to aperiodic functions as well. What he really said was that if you have an aperiodic function, it can be thought of as the sum of several sinusoids with infinite number of frequencies, infinite number of such small components, each with vanishingly small amplitude. And if you put all of them together, you will get the given aperiodic function. So, let us see how we go about splitting up a given aperiodic f of t into various sinusoidal components of the description which we gave just now. The key to the whole idea is that if a particular aperiodic function is given, we can assume that the period is infinity, extending from minus infinity to plus infinity. And what happens beyond plus infinity on one side, what happens below minus infinity on the other side, we do not bother about it. So, if any aperiodic function can be thought of as a periodic function with a period extending from minus infinity to plus infinity, it occurs just once. So, that means the period of this is going to be infinity. What is the consequence? The consequence is that the frequency of this is 0, and so if the frequency of this 0 is 0, then how are we going to think of various harmonic components, because in the Fourier series various frequency components that are present are integrally related, integral multiples of the fundamental frequency. Here the fundamental frequency is 0, and in the Fourier series the only term which is the fundamental frequency whose frequency is 0 is the DC term, and after all a DC term can't fit any aperiodic function. So, we must look for a different approach altogether. So, let us see how we develop this. So, basically the key idea as I mentioned is that we think of the period of this aperiodic phenomenon to be infinite, extending from minus infinity to plus infinity. So, what we will do is we will start with the Fourier series of a periodic function and then see what happens when the period becomes larger and larger till it goes out to infinity. So, in the limiting process we will find out how the various frequency components arise and what their amplitudes will be and so on and so forth. So, let me start with a function which is periodic period T naught. Just to give a concrete example, I will take a specific waveform, but all our discussion will be in completely general terms. So, we have a periodic pulse train of amplitude A and pulse duration d and the periodicity being T naught. We know the spectrum for this would be something like this, where this is C n and we know that C of n is A d upon T naught sin n omega naught d upon 2 by n omega naught d upon 2. This is something which we have talked about several times. So, let us look at the spectrum, and since this is going to be a real number, C n is because the function is even, so it is going to be a real number. I am not plotting the phase and the magnitude separately, I am plotting the entire C n itself directly. So, it is either it is always real, either positive or negative. The height of this is A d upon T naught, and the first 0 occurs when n omega naught d by 2 happens to be pi. Therefore, the frequency corresponding to this is 2 pi upon d. So, this is the nature of the spectrum for a periodic pulse train like this. And if we wanted to find out f of t from this, we certainly write this as n from minus infinity to plus infinity of C n e to the power of j n omega naught t. That is what you get. This is the general term that we are getting. This particular C n that we are getting applies to this specific waveform. This is the general formulation. The general formulation for C L in a general case would be 1 over T naught minus T naught upon 2 to plus T naught upon 2 of f of t e to the power of minus j n omega naught t dt, as we already know. So, these are the two general expressions for C n, and this is the f of t, which is the Fourier series for this waveform. So, these are two general expressions. In the particular case of a periodic pulse train, this would be the particular value of C n that we derive for our special case that we have considered. Now, let us see what happens when we have a periodic pulse train, a periodic function again, but the period becomes very large period. I will simply say T naught of L to indicate that it is a large period. We have the same waveform, but the period becomes very large. So, I can put this in this fashion. I have the same pulse of amplitude A, duration d, but the period is very large. That means the next pulse occurs after a long period. Very large period. So, consequently, I will say the angular frequency corresponding to this, the angular frequency here is fundamental period angular frequency is omega naught. So, we will say fundamental of this is delta omega naught, I will say. So, to emphasize that it is a small angular frequency delta omega naught. So, T naught of L is 2 pi over delta omega naught. So, what would be the consequence as far as the spectrum is concerned? Now, look at this. This is the formula for C n. Now, what happens if T naught becomes larger and larger, A d upon T naught becomes smaller. That means, the initial height here, the amplitude will become smaller. And if you have very large T naught, this becomes almost negligible, smaller and smaller. I am sorry, what we should say is, I am talking about C n not as a continuous thing. C n's will be, this is the envelope. What we have drawn is the envelope. The actual C n will be at discrete points on this, with the spacing between two lines being delta omega naught, the fundamental frequency omega naught. This is what we had in the first place. What I have drawn here is the envelope of C n. So, the actual C n's will be present only at discrete points, and this is a line spectrum. And the spacing between two adjacent components is omega naught. Now, when we make the period larger and larger, keeping the pulse width the same d, what you have is A d upon T naught becomes smaller, very small. So, the result is that after all 2 pi by d remains invariant, because the 0 occurs here when n omega naught d by 2 is pi, and that corresponds to 2 pi upon d, and therefore, what you are having here is therefore is that you will have if you plot C n, the envelope will be like this. And what happens to the lines? Previously, the separation between two lines is omega naught. Now, since the fundamental frequency is delta omega naught, which is smaller, the lines come closer and closer. Lines come closer and closer. The lines become closer and closer, the whole amplitude comes down. Now, what we really want to know is what happens when T naught goes to infinity, because we want to treat an aperiodic function as a function of infinite period. So, if T naught becomes infinitely large, then obviously this whole thing crashes down to horizontal line, because the amplitude becomes 0. So, that will not give us any useful information. So, we must see some other way of handling this information. So, what we should like to see is have some kind of new quantity which we could plot, which will not become 0, which will be meaningful and which will give us an idea of the relative sizes of the various harmonic components. So, to do this, what we will think of is, instead of C n, after all the whole problem in here has come because C n has 1 over T naught upon this. So, C n is the Fourier coefficient. It represents to us the amplitude in a sort of fashion of the e to the power of j n omega naught t term. Instead of that, if I plot C n times T naught, so in our case is T m times T naught of L, this I can write this as C n times delta f naught, because if delta omega naught is the fundamental angular frequency, delta f naught is the corresponding frequency. So, I can write this as C n upon delta omega naught upon 2 pi. So, if you plot this quantity, you are going to multiply this C n by T naught of L. That means, you are as far as this particular waveform is concerned, you are multiplying C n with T naught, then you are going to plot A d sin n omega naught d by 2 upon n omega naught d upon 2. Therefore, the spectrum will now be restored to its original size. So, what you are plotting now will be having this envelope which is exactly the same as this, but the lines will become come closer and closer, and what we have plotted here is C n times T naught of L, large T naught, and the amplitude will be, since A d is multiplied by T naught, this will be A d, and the spacing between two particular lines becomes delta omega naught. And this frequency corresponds to 2 pi upon d, because that is not changing, d is the same. So, we now see that if you do not want to deal with C n, but C n times T naught of L, then we can think of a meaningful way of representing the various harmonic components and what is the relative size. Since this is C n, the coefficient per unit frequency, this is called coefficient density, whereas this is the Fourier coefficient, this is called Fourier coefficient density. This is called the coefficient density, and once you have this concept of coefficient density, then f of t can be written as, further I will write it here, f of t can be written as, you recall f of t is the Fourier series expansion is this n minus infinity to plus infinity C n e to the power of j n omega naught t, but instead of C n I would like to talk in terms of the coefficient density. So, I will write this as C n upon delta omega naught over 2 pi e to the power of j n omega naught t sum from n equals minus infinity to plus infinity, and since I have divided by delta omega naught by 2 pi, I have to multiply by delta omega naught, and then I have to write here 1 over 2 pi. So, that would be the form of the Fourier series now in terms of coefficient density rather than the coefficients. Now, let us see what happens when you have an aperiodic function. So, in the aperiodic function we still take this same function of same pulse of amplitude A, duration d, but there is no other pulse involved, the period is infinity. So, infinite period. So, imagine that we have this situation here, where now delta omega naught tends to 0. So, what is this consequence of this? T naught goes to infinity, delta omega naught becomes smaller and smaller. So, what happens to the spectrum now? AD is independent of your T naught. So, that remains the same. This 2 pi by d remains the same. All that happens now is, as you increase the period, delta omega naught becomes smaller and smaller, these lines come closer and closer, there will be more lines, and in the limit you will find a particular line at every point on the x axis. So, that in other words, you will get a frequency component at every point on the x axis rather than at discrete points along the x axis, because delta omega naught becomes smaller and smaller. So, the lines get crowding, come almost next to each other at every point on the curve, and therefore, we can say n delta omega naught, which what is n delta omega, what is the significance n delta omega naught? N delta omega naught is the frequency at which a line exists in the spectrum. Now, a line theoretically exists at every point on the spectrum. So, n delta omega naught can be replaced by a continuous running variable omega. So, that is how the limiting process occurs. As the fundamental frequency becomes smaller and smaller, the harmonics exist at every point along the omega axis. So, in the limit you will have a frequency component at every point along the omega axis. So, the spectrum now would be just like this, but a continuous spectrum, because you have at every point there is a meaning for this amplitude. So, this is a continuous spectrum. And at DC value here it is AD, and the x axis is in terms of omega as before, everywhere it is omega. This is n omega naught, of course, here this is n delta omega naught, and here it is running variable is omega, right. So, what we have here is an arrangement where you have every frequency present, but the coefficient density corresponding to each frequency is different, that is dictated, that is given by the spectrum. So, now let us see what happens. The coefficient density is now Cn times T naught L, whatever we are having is called now f of j omega. That is f of j omega. How do we get now f of j omega? Here you observe that in the Cn is given by this formula. The coefficient density is obtained by multiplying Cn by T naught. So, once you multiply Cn by T naught, what you are having is the integral relation for this is minus T naught upon 2 to plus T naught upon 2 f of t e to the power of minus j n omega naught t dt. So, in our case it happens because T naught is multiplied by this. So, what you have is it is this formula applicable to the aperiodic case, and what is the period? T naught by minus T naught upon 2 and plus T naught upon 2 are infinity. So, you are integrating f of t multiplied by something over a complete period which is extends from minus infinity to plus infinity, f of t and e to the power of minus j n n omega naught now in the first case is replaced by n delta omega naught here, and when you go to the aperiodic case n delta omega naught is a continuous running variable omega naught. Therefore, this will be f e to the power of minus j omega naught dt. So, the coefficient density in the aperiodic case will be f j omega, which is minus infinity to plus infinity of f of t e to the power of minus j omega t dt, and this is called the Fourier transform of f of t. This is called the Fourier transform of f of t. Now, what is the corresponding result for the Fourier series? That means, Fourier transform is the equivalent of what we had for C of n. The formula for getting the Fourier coefficient, we had some formula. The corresponding formula here is the Fourier transform. Instead of C n, we deal with f of j omega. Why? I will explain for a moment later about the notation. Now, what is the result that you have corresponding to this? F of t in the periodic case is expressed as the sum of different exponential functions. Now, what is it that we have here? F of t, as you recall, in the case of a large period is this. So, now we have to take the limit of this as delta omega naught goes to 0. So, limit of f of t, limit of this series as delta omega naught goes to 0 means we have to take the integration. After all, C n over delta omega naught by 2 pi is f of j omega. This is f of j omega. Therefore, we have to write here as f of t. I will write this here. Limit as delta omega naught goes to 0 of 1 over 2 pi the summation of C n over delta omega naught over 2 pi, we call that f of j omega. So, f of j omega e to the power of j omega t, because n omega naught becomes n delta omega naught becomes, I am sorry, here also I must have delta omega naught in the large case. N delta omega naught becomes omega, and then this is delta omega. And the frequency omega, because n from minus infinity to plus infinity, that means omega is minus infinity to plus infinity. So, that really becomes 1 over 2 pi. So, that summation in the limit becomes integration from minus infinity to plus infinity on omega f of t e to the power of j omega t d omega. This is f of t. So, what do we have? This is f of omega. I am sorry. This must be f of j omega. This is f of j omega. So, instead of a Fourier series for f of t, instead of f of t being thought of as a summation of several exponential functions like this, what we are really having is f of t is consisting of similar exponential functions e to the power of j omega t, where omega can take any value from minus infinity to plus infinity. Each of these is multiplied by a coefficient which is f j omega d omega by 2 pi, and you are integrating that over the complete omega axis from minus infinity to plus infinity. This is f of t, and this is called the Fourier integral. This is called the Fourier integral. So, instead of the series you have an integral, and instead of a formula like this for calculating the Fourier coefficient, you are calculating the Fourier coefficient density, which is referred to as the Fourier transform. Now, a few words about this, why we get this 2 pi here. This 2 pi arises because we are calculating the Fourier density, coefficient density in terms of frequency rather than omega naught. So, this is how it is conventionally defined, Therefore, because we are talking about the coefficient density in terms of having the denominator as a frequency rather than in hertz rather than radians per second, we get this 2 pi term. And secondly, we call this f of j omega instead of f of omega, because later on we would like to relate this to the Laplace transform, where this f of j omega can be thought of as a special case of f of s. We deal with a Laplace transform domain. Therefore, it would be convenient for us to put this f as j omega, because after all when we talk about the exponential terms here, every j is accompanied by every frequency is accompanied by j. So, j omega would be all right. You can think of it as f of omega as well, but f of j omega would be more convenient for us to use. Now, let me quickly summarize what we have done up to this stage. We started with a periodic function. The formula for finding the Fourier coefficients for the periodic function is this, we know general function, and once we have the various coefficients, we can construct the f of t by combining all such exponential terms from minus infinity to plus infinity. This is the Fourier series, and this is the integral that we use for calculating the Fourier coefficient. Taking a particular case of a periodic pulse train, we showed that it has a spectrum like this, and the characteristic of the spectrum is that it is a line spectrum. You have coefficients only at integral multiples of the basic frequency. Therefore, the spacing between two adjacent lines is the fundamental frequency omega naught in radians per second. Now, then we inquired as to what happens if we keep this particular pulse constant at the center, centered around the origin, and allow this t naught to become larger and larger. So, that is a transition before we go make t naught equal to infinity to see the trends. So, as t naught becomes larger and larger, we observe that the amplitudes of these various Cn coefficients become smaller and smaller. So, this spectrum, line spectrum that we had, becomes shallower and shallower. It will be of this order, it will be like this, and the height will diminish as t naught increases further. But another fact that we noticed was the spacing between the lines now, instead of omega naught, which was the fundamental frequency earlier, becomes smaller and smaller, because as t naught increases, omega naught becomes smaller and smaller. But this is not meaningful to us in the limit when t naught becomes infinity, because when we are moving towards a direction in which the period is to be considered to be infinitely large. So, if the period is going to be infinitely large, this whole thing becomes 0, and this Cn term will become 0, and therefore, we will now have no way of knowing what is the relative sizes of two different frequency components. So, to beat this problem, what we said was, instead of talking about the Fourier coefficient Cn, let us talk about Fourier coefficient density, which is Cn divided by d delta f naught. So, if you recourse to this new quantity, which is Cn times t naught, the period, then immediately the trouble that arose because t naught being the denominator will vanish, and then we had Cn t naught will be minus t naught upon 2 t naught upon 2 f of t to the power of j n omega naught t dt, and immediately the spectrum would be like this, corresponding to this periodic pulse train. So, you have, depending upon the pulse width and amplitude, you have a certain value a d, and this no longer, as period becomes larger and larger, this no longer has to become smaller, a d will remain the same, the lines will become closer, and the spacing between two adjacent lines is delta omega naught, which is the new fundamental frequency, which is quite small, and we can put f of t as 1 over 2 pi times this coefficient density times e to the power of j n delta omega naught t. I will write this as times delta omega naught. So, the Fourier series now will be in this form, but instead of Cn we are talking in terms of the coefficient density. Now, at this stage we take the limit as T naught becomes infinitely large. So, if T naught becomes infinitely large, we observed that delta omega naught becomes smaller and smaller. That means the spacing between lines becomes 0 to in the limit you will have a frequency component at every point on the omega axis. So, what we started as with a line spectrum now becomes a continuous spectrum. That means almost every single frequency is present. Of course, almost every, because at this point we can say this is 0, but nearly everywhere you have a frequency component present. And what we are plotting now is not anymore the Fourier coefficient CL, but the coefficient density. And we give a new name for that coefficient density, we call that f of j omega, the Fourier transform, which is given by the formula minus infinity to plus infinity of f of t e to the power of minus j omega t dt, that is f of j omega. To recover the original function f of t from the f of j omega, instead of the Fourier series we will have now take the limit of the summation as delta omega tends to 0 of 1 over 2 pi times the Fourier coefficient density times e to the power of j omega t delta omega, and that leads us to the formula like this, which is called the Fourier integral. So, basically then we have, when you are dealing with the Fourier transform and for an aperiodic function, we have two basic integrals to deal with. From the given f of t we can generate this Fourier transform, which is really Fourier coefficient density as explained here, and once you have the Fourier transform we can recover the function of time through this integral. So, these are the two basic integrals for characteristic of the Fourier integral theory. Now, we will look into the meanings of the coefficient density and the similarities and the contrast between a periodic function and a aperiodic function in greater detail at this point of time.